Hello guys, I'm Albert, and today I will be talking about vectors. According to the New Oxford American Dictionary, a vector is a quantity having direction as well as magnitude, especially as determining the position of one point in space relative to another. As you can see from the graph above, the vector AB, in order to express a vector, you can write it as capital letters with the tail and arrow pointing to the right side above the letters. Next, how do we calculate vectors? We should break the vector up with two parts, the x and y components. Also, in order for us to find the location of the vector, we can translate the point to the original or on a Cartesian plane. A vector also has heads and tails. The head is where the vector is pointing, and the tail is where it starts, or the starting point of the vector. To find the coordinates of a given vector, we would have to translate the point out to its origin, which is 0, 0 on a Cartesian point. The head of the vector would be the point that I call f1, f2. To find the components of the vector f, we would subtract the components of the origin from the vector f1, f2. Straightforwardly, the components of vector f would be f1, f2. The magnitude of a vector is the length of a vector. We can use a formula that's formulated from the Pythagorean theorem. By adjusting the distance formula, we have used to find the distance between 2 points. I found a new formula to directly calculate the magnitude of a vector, which is square root of the x component squared plus the y component squared. I applied the formula to example of vector f. Vector f has a component of f1, f2. So first we have to square f1 and add it to f squared f2. Then we would square the entire thing. To present a magnitude of a vector, we use two vertical bars on each side of the letter. So what is the magnitude of vector f? The magnitude of vector f is presented as square root of f1 squared plus f2 squared. The direction of a line is the slope of a line from a directed line segment. From the Cartesian point above, there's a vector. The direction of the vector once is presented through the slope. And we can find the slope of the vector using the formula y2 minus y1 over x2 minus x1. To simplify this process, since the components of the vector is already the change in x over the change in y, we can just simply divide the y component of the vector by the x component, which in other words is change in y over the change in x. So if the vector is x, y, the slope is just y over x. This formula is used to find the direction of all vectors. An example of this is we can use the origin in the point 8, 9. The directed line segment will be pointing at the slope of 9 over 8, which is the direction of the vector. Now we'll be talking about the arithmetic of 2D vectors. This includes the adding and subtracting of vectors. This is a very simple process. We can add vectors by adding the x components together and the y components together. Graphically, if we're to add vectors together, we have to apply the tail of the vector to the head of the other vector, making the new vector from the tail of the first vector to the head of the second vector. Mathematically, we just have to have the respective components together. From the diagram above, we can see that we have the vectors 1, 2, and 6, 7 on a Cartesian point. And as you can see, we have to connect the tail of the vector to the head of the other vector, so that addition can be valid. Next, from the diagram, we have to add the x components together, which is 1 and 6. Then we have to add the y components together, which is 2 and 7. After we add these two vectors, the process should look like this: 1 plus 6, 2 plus 7. Therefore, the answer is 7, 9. Subtracting vectors is the same as adding vectors, but we have to reverse the vector we want to subtract from the original vector. From the set of vectors above, we can see that we have reversed the vector, and the ultimate answer will be 1, 2. We will be moving on to 3D vectors now. If it is a 3D vector, we have to break the vector up into three parts, the x and y and z components. And in order to find the location, we have to locate it back to the origin of a 3D point. To find the magnitude of a 3D vector, it's the same process. We have to add a z component near the end of the y component. Since in 2D vectors, the magnitude is only x and y components. A 3D vector also has heads and tails. The head is where the vector is pointing, and the tail is where it starts, or the starting point of the vector. To find the coordinates of a given vector, we have to translate the point onto the origin, which is 0, 0, 0 on the 3D plane. And assuming that we have the vector f1, f2, f3, the process is the same as 2D, so we have to subtract the origin from this vector, and the coordinates of vector f would be f1, f2, f3. There are more than two dimensions when it comes to vectors. Next is the arithmetics of 3D vectors. Adding and subtracting 3D vectors has the same mechanics as the process of adding and subtracting 2D vectors. To add 3D vectors, we have the vector of 3, 4, 5, and then another vector of 3, 4, 5, 6. We have to add the x components with the x components, y with the y components, and the x with the x components. This would be 3 plus 4, 4 plus 5, 5 plus 6, and the result would be 7, 9, 11. To subtract 3D vectors is also the same. For subtract 3D vectors is similar to the subtraction of 2D vectors too. We have to reverse the vector we want to subtract, and using the same set of vectors, which is 3, 4, 5, and 4, 5, 6. If we want to subtract 3, 4, 5, and 4, 5, 6, it will be 4, 5, 6 plus negative 3, 4, 5. Then it would be 4, 5, 6 plus negative 3, negative 4, negative 5. Therefore, the result will be 4 minus 3, 5 minus 4, and 6 minus 5, which is 1, 1, 1. 4D vectors work the same way when it comes to addition and subtraction. As we've learned previously, we can add and subtract vectors. We can also multiply vectors, in the process of multiplying vectors is called scaling a vector. The difference between a vector and a scalar is that a scalar does not have a direction, while a vector has both a direction and a magnitude. The overall purpose and outcome of multiplying a vector by a scalar is to change the size of the vector. A good example of this is shown above when we have a vector 5, 4 and scale of 10. To multiply a vector by scalar, we simply have to multiply the x and y components and the vector to the scalar. Therefore, the x component would be multiplied by 10 as well as the y component. 5 multiplied by 10 is 50, and 4 multiplied by 10 is 40. This new vector is 50, 40. It's 10 times longer than the original vector, which is 5, 4. To flip the direction of the vector, we have to multiply the vector with a scale of -1. This will not change its size, but will flip the direction. The dot product in 3D vectors is multiplying the respective components together and adding them together. And the final sum will be the dot product. As shown with these two set of vectors, we use these calculations above, and the answer is 62. If the dot product is 0, it will be perpendicular. Using the vectors shown and due to the calculations we have used, we have found that the dot product is 0, which means that these two set of vectors are perpendicular. This is a practice problem for you guys to review what we have learned. Here's what we have to find out. To find the vector between Albert and the beach, we have to use subtraction of vectors, which is 9, 13. Here's the second part. Since the magnitude is the length, by using the formula, we have found that the answer is 5√10. Here's the third part. Due to our prior knowledge of subtraction of vectors, we have to reverse the final point and to add it to the first point, which equals 5, 8. Here's the fourth part. To do this part, we have to find the magnitude of the vectors. If we know that the magnitude of the vector or Albert's position is square root of 250, the magnitude of the struct vector is square root of 16 plus 25, which is square root of 41. Here's the scalar problem. To do this, we multiply Albert's vector from its position to Beatrice's scalar of 1/3. This would be 9 times 1/3 and 13 times 1/3. Therefore, the result would be 3, negative 0.43. Albert's position is 3, 0.43 when he intercepted a shark.